here at the ASC. He works in solar physics in the solar physics group. And his research focuses on polarized radiation, its genesis and its transfer in the sun. Also in the studies of the numerical synthesis. He was a student here at the house. He did his PhD in 2018. Then he went for a postdoctoral research position in Switzerland, I think, in Locarno, right? In the Institute Ricerche Solari Locarno in Switzerland. And then since 2021, he came back to the AAC, first at the Paul Mac Group, and now under the umbrella, I think, of the Whole Sun Synergy ERC grant, right? So welcome. Thanks for accepting our invitation. The floor is yours.
So first of all, thank you for inviting me to give this talk. Thank you all for taking time out of your day to come for coming. And well, today I'm going to talk to you about a research from a couple of years ago about the resolution of the solar sodium D1 polarization paradox, and also some results since applied to other solar D lines of diagnostic interest. So as many of you know, many of the open questions in solar physics are intimately linked to magnetic fields, such as the heating of the solar corona or the triggering of explosive events pictured here. Now, thus it is very important to get information about these magnetic fields. Although some remote measurements can be made in the heliosphere, the vast majority of the information accessible to us is remote through the radiation in spectral lines. Different spectral lines encode information on different depths of the solar atmosphere, as pictured here. Moreover, if our interest is specifically on magnetic fields, they leave their properties on the polarization of spectral lines. The polarization properties of radiation are univocally determined by the 4 Stokes parameters, which are differential measurements of the specific intensity, applying filters that select for different polarization states. Thus, Stokes I gives us information on the full specific intensity. Stokes Q and U together give us the orientation and degree of linear polarization. And Stokes V gives us the circular polarization. Now, there are a variety. Polarization should be expected whenever in the physical processes that emit radiation, there is some asymmetry, some breaking of symmetry. Here in this talk, I'm going to focus specifically on those related to magnetic fields. And first of all, I'm going to discuss the polarization produced by the Zeeman effect. Here, for simplicity, I'm showing the case of a 2-level atom whose lower level has J equals 0, and its upper level has J equals 1. In the presence of an external magnetic field, these are split into various magnetic sublevels. Well, the ones of the upper level which can carry magnetic sublevels. Now, different transitions between different M levels carry different polarization properties. And due to this splitting of magnetic sublevels, they are shifted in frequency between one another. Because of this, they no longer cancel. And instead, we find polarization patterns that depend on wavelength. If the magnetic field is longitudinal to the line of sight, parallel to the line of sight, then we find circular polarization. And if it is transverse to the line of sight, perpendicular to the line of sight, we get a linear polarization pattern. The amplitude of these patterns depends on an R parameter, which is the ratio of the magnetic splitting over the Doppler width, which depends on the wavelength of the considered spectral line and the magnetic field, among other things. Now, the circular polarization amplitude, scales as this parameter, while the linear polarization scales as its square. And therefore, it should be expected only for much stronger magnetic fields. In addition, because of this dependence on wavelength I was discussing, we typically get larger R parameters and therefore more sensitivity to the Zeeman effect for infrared lines than for ultraviolet light. On the other hand, and more important to this talk, I want to talk about another physical mechanism, which is scattering polarization. That is the linear polarization that is produced by by scattering. In this case, I'm showing you a toy example of a 90-degree scattering, in which, here shown with oscillator models, at 90-degree scattering, we get a fully linearly polarized scattered radiation. Now, in the solar atmosphere, we have anisotropic radiation, which is largely anisotropic around the radial direction, so that would be approximately the symmetry axis. And this is because of the stratification, mainly because of the stratification of the properties of the solar atmosphere. Because of this, the atoms that are illuminated by this anisotropic radiation perceive a net angular momentum, which causes an imbalance of the populations of different magnetic sublevels. Now, as I mentioned before, transitions between different magnetic sublevels produce different polarization properties. And this results in a net linear polarization, which is the scattering polarization itself. Furthermore, magnetic fields modify this atomic polarization, typically by destroying it, and this leaves signatures on the resulting scattering polarization by depolarizing it in the case of a 90-degree scattering, and also rotating the plane of linear polarization. Now, for levels with a longer lifetime, the magnetic field has more time to destroy this atomic polarization before the excitation, and therefore they are sensitive to weaker magnetic fields. Indeed, the Hanel effect operates when the magnetic splitting of the level is comparable to its natural width, given here by the oscillator strength or the Einstein coefficient. This allows us to derive the so-called Hanel critical field, which is proportional to the Einstein coefficient and therefore inversely proportional to the lifetime of the level under consideration. And well, as I said, scattering polarization is typically found for large inclinations, and therefore it is found typically in more abundance when observing close to the limb. Here, here I want to show you one of the observations that kicked off the so-called solar D1 sodium paradox, which were some observations taken at Kitt Peak with the ZIMPOL imaging polarimeter. And here I'm showing the sodium D lines in intensity, D2 and D1. And now I'm blowing up the lower panel, and you can see the linear polarization, the scattering polarization in D2, and most notably the D1 line. This came as a surprise because this line was expected to be unpolarized for reasons I'll explain in just a second. Further observations showed that indeed this was not a fluke. Other observations with ZIMPOL, other observations at Temis also showed a significant D1 polarization. And now I'll go into the reason why it was not expected to be polarized. This comes from the atomic system that produces these D lines, which are transitions between a two-term atomic system, whose lower level has orbital angular momentum L equals 0, and its upper level has L equals 1. When we account for the spin, the upper level is split into two fine structure levels, which have J equals 3/2 and J equals 1/2. These are respectively responsible for the D2 and D1 line transitions. Now, for the D1, both the upper and lower levels have J equals 1/2, which means they can only have magnetic quantum numbers 1/2 and -1/2. For this reason, they cannot carry the atomic polarization necessary to produce the linear polarization. However, in atoms such as sodium, we also have nuclear spin and therefore hyperfine structure. Because of this, the various components of the D1 line and D2 lines are split into various hyperfine structure components, each with their own frequency, which is slightly shifted with respect to the others. Furthermore, now each of the hyperfine structure levels is characterized by an angular momentum F. As we can see, these are larger than the fine structure levels. And for the lower levels, we see F equals 2 and F equals 1. which can carry atomic level polarization. This, 1 year after the initial observations, led to the publication of a seminal letter in Nature, in which it was discussed that the solar D1 could be reproduced remarkably well by accounting for by some lower level atomic polarization. Now, this was it was solved in a relatively simple manner, imposing radiation field anisotropy that was flat with wavelength and which varied with a height scale factor. And also some lower level polarization was added. And again, with this, the D1 line could be reproduced to a good degree. However, this posed a problem because as I mentioned, long-lived levels are very vulnerable to the Hanley effect. And indeed, for the ground state of sodium, one would expect that magnetic fields of only tens of Gauss of tens of milligauss, sorry, would destroy this polarization completely. However, there is ample evidence that such magnetic fields are found throughout the solar atmosphere. Here, just to name a few evidences, we have observations in other lines, such as in the calcium resonance line, and also from plasma physics arguments, which suggested that stronger magnetic fields should be ubiquitous. This led to the so-called paradox of the solar line polarization, because if this was produced by lower level atomic polarization, then this was incompatible with the expected magnetic fields in the sun. This paradox even led certain scientists to question the established theory of radiation-matter interaction. This led to theoretical research, studying atomic systems excited by either monochromatic or broadband radiation, and laboratory experiments, again considering monochromatic lasers and spectrally flat light, sources of light. And now I want to discuss a breakthrough that came a few years later. And to discuss this, first I want to point out that in previous modelings, the ones I had discussed before, the radiation field had been assumed constant over the wavelength interval spanned by these various hyperfine structure transitions. So they would all see the same radiation field. However, a few years later, my colleagues Luca Belluzzi and Javier Trujillo Bueno proposed a new physical mechanism, which I will refer to as the key mechanism, which relied on accounting for the variation of the intensity and anisotropy of the radiation field within these narrow intervals. Indeed, here I'm showing a radiative transfer calculation I carried out some time ago around the formation region of sodium, in which the vertical blue and red lines show the wavelength intervals in which the hyperfine structure transitions are found for the D1 and D2 lines. The black curve shows the radiation intensity, and the green curve shows the anisotropy of the radiation field. And indeed, you can see that the anisotropy varies a fair amount even between these narrow intervals. So in order to consider this in our calculations, we need to account for the frequency correlations between incoming and scattered radiation in scattering processes. This is known as partial frequency redistribution. And indeed, in the calculations we consider, this is one of the most numerical intensive aspects. And here are some results for my colleagues at the time. And I want to draw your attention to panel C, where here we see the linear polarization produced in the D1 line. And indeed, by accounting for this physical mechanism, by the variation of the anisotropy within the window spanned by the various hyperfine structure components, some linear polarization could be produced. The black and the solid and dashed curves are simply calculations in different atmospheric models. Now, this was already a breakthrough, but it was not the end of the story, because it still needed to be demonstrated that these signals would survive in the presence of magnetic fields. And this led me and colleagues develop a numerical code, a radiative transfer code that could take into account all the necessary aspects to include this key mechanism and magnetic fields. For simplicity, we considered plane parallel or one-dimensional atmospheric models. And of course, we had to consider a two-term atomic systems that included hyperfine structure. Also, as mentioned, we had to account for partial frequency redistribution, or the frequency correlations between incoming and scattered radiation. And of course, the magnetic fields, accounting for the Handel effect, for the Zeeman effect, and magneto-optical effects, which I will not discuss in this talk. Also, we accounted for the possibility of the depolarizing effect of elastic collisions. And here I'll just cut to the chase and show you the final results of these calculations compared to observations. And with the black curve are some observations taken at IRSOL using ZIMPOL, while the red line, the red dotted line are calculations in the absence of magnetic field. And the blue curve represents calculations including an isotropic distribution of magnetic fields. So what we see is that the D1 line survives in the presence of these magnetic fields. So it's not depolarized by magnetic fields. And indeed, considering both the D2 and D1 lines, we see that we get a better agreement with observations when accounting for these magnetic fields. So this in itself would represents what we wanted to find, the solution of this paradox. Now, if you indulge me, I'll go into some more technical aspects. And here I'll show you some radiative transfer calculations in which the vertical axis the Z vertical axis represents the radial direction of the sun. And the line of sight is given with respect to it's given by its inclination with the vertical. In this case, we take a very inclined line of sight to get large scattering polarization signals. This is what we see in the absence of magnetic fields, that we only get Stokes Q. And now I include a vertical magnetic field. With a small field, you see in the D1 some depolarization and the appearance of an increase in the D2 line. This is associated to accounting for hyperfine structure. This is just a technical detail. And also, for stronger magnetic fields, still we get the appearance of some Zeeman effect. On the other hand, here is the same thing, but with a horizontal magnetic field instead of a vertical. And here, what we see is a depolarization of D1 and D2, and the appearance of Stokes U, which was the linear polarization measured at a different axis. So what we're seeing here is a rotation of the plane of linear polarization. The appearance of these signals in the wings is due to the so-called magneto-optical effects, which I don't have time to go into. But anyway, I was showing you this just to explain that when I was considering this isotropic distribution of magnetic fields, what I was actually doing was carrying out several calculations with these different orientations and considering at the end a weighted average of them. So this isotropic distribution is really just the realization of several orientations of the magnetic field along along a sphere. 64 realizations to be precise. Anyway, the last thing I want to discuss about the sodium D1 line is the depolarizing effect of elastic collisions, in particular elastic collisions with neutral hydrogen. And though we included them, and indeed in the red curve, I showed them considering an unrealistic high rate of depolarizing collisions, we saw that they did not have any appreciable effect on the depolarizing rates. This is due to where these lines form, which is the middle chromosphere, where the density of hydrogen is already quite low, and so they do not meaningfully depolarize. So to summarize the findings of this part, the D1 scattering polarization signal can be well reproduced by accounting for the key mechanism, namely the variation of the intensity and anisotropy of the radiation field over the wavelength interval spanned by the various hyperfine structure components of the D line. Also, these signals survive in the presence of a magnetic field for strength expected in the quiet solar chromosphere. And both of the D1 and D2 lines are sensitive to the presence of Gauss strength magnetic fields, although sensitive in different degrees and to different extents. The profiles of both D1 and D2 appear to be completely insensitive to the depolarizing effect of elastic collisions. So this leads us to the conclusion that these findings provide a satisfactory resolution to the D1 paradox. Indeed, the polarization signals can be reproduced with the available theories of atom-photon interaction, even considering that the chromosphere is appreciably magnetized. This magnetic sensitivity opens a new diagnostic window for probing the magnetic fields in the quiet solar chromosphere because of this differential dependence of D1 and D2. And this is of particular interest in the present new era of large aperture telescopes, such as the KIST or the upcoming EST. And indeed, further investigations of interest would be considering 3D atmospheric models, dynamical models that include the effects of velocity. And with this, we would expect to be able to reproduce a wider variety of the observed patterns of the sodium D1. And with this, I finished the discussion on the sodium, on the part of the sodium D1 line. But with these findings, I want to discuss also the results applied to other solar D lines of interest. In particular, the potassium D lines and the barium 2 D lines. Indeed, for the sodium D lines, the two are separated. So why I call them D lines is because they're produced by a similar atomic model. That is a two-term transition whose upper levels are split into two fine structure levels, and at least some of the isotopes of these species present hyperfine structure. So we could expect this key mechanism to apply. Also note that while for the sodium D lines, the two are separated by about 6 angstroms. For potassium, it's more 34 angstroms. And for the barium, it's almost 380. This is because of different separations between the fine structure levels. And another notable difference between these the D lines of these species are their formation depths. Here is a rough estimate of these formation depths based on where the optical depth is equal to unity. So here I'm showing it for the sodium D line, which forms in the middle chromosphere. Here for the barium D lines, which form a bit deeper. And here for the potassium D lines, which form around the temperature minimum of the sun, which is the interface between the solar photosphere and solar chromosphere. So first I want to discuss some relevant aspects of the barium D2 lines. Now, barium D2 has 7 stable isotopes, but only 2 of them have hyperfine structure. By abundance, this accounts for 18% of the total. But the isotopes that do have hyperfine structure have a much larger separation between the hyperfine structure levels, more than 1 order of magnitude larger, almost 1 order of magnitude, larger than sodium. Now, another complication of the barium D line is that apart from the 2 terms I was discussing before, it also has a metastable term of lower energy than the upper level of the transitions. Now, for the code I was using before, which for simplicity I'll call our code, now this could only account for a 2-term atomic system. So it would not be suitable for accounting for these for this atomic system. For this reason, we made use of the Hanley-RT code developed by my colleague Tanausu del Pino Aleman, which can account for partial frequency redistribution, magnetic fields, and a multi-term system. However, at present, or at least at the time that these investigations were being carried out, it could not yet account for hyperfine structure. Nevertheless, this could be taken into account by making some substitutions in the quantum numbers, which are strictly applicable in the absence of magnetic fields. And here I show you the results in intensity and in linear polarization, both accounting for metastable levels and neglecting them. Now, the metastable levels play a negligible role in intensity, while in the linear polarization, the scattering polarization, they do depolarize it, the metastable levels, although they do not significantly affect the shape of the signals. Now, until we have a code that can account for multi-term atoms and hyperfine structure and magnetic fields, we considered an investigation accounting, making these calculations, saying, yes, we're aware that there is some impact of the metastable levels, but still let's investigate what happens with the magnetic fields. Oh, by the way, notice that this amplitude is significantly larger than the one that was shown for the sodium D1 line, which was, well, about 1 order of magnitude smaller. This is because these patterns also appear because of the key mechanism, but the hyperfine structure is larger. And so we get more variation of the radiation anisotropy within the window spanned by the various hyperfine structure transitions. Okay, and with this, I show you the calculations with our code, the 2-term code with hyperfine structure, accounting for the impact of isotropic magnetic fields. And well, just to show you that for magnetic fields on the order of tens of Gauss, we do get a clear sensitivity to these magnetic fields in the case of an isotropic distribution of magnetic fields through a depolarization. Now, another interesting thing was that we considered calculations considering various atmospheric models. These were simplified 1D semi-empirical models, but they give us information of what would be expected in different regions of the sun. And we find that the differences between these patterns are very small. What this indicates is that the variation in the scattering polarization would depend on the magnetic field. Of course, these calculations will have to be carried out considering more sophisticated 3D atomic models and considering a code that is capable of accounting for a multi-term code with hyperfine structure. But still, this is an interesting finding. Also, I want to show you the results of the circular polarization, considering here an inclined magnetic field and an inclined line of sight, so that we have a large longitudinal component of the magnetic field, which produces circular polarization. And indeed, here are the results of the circular polarization, which we found to increase in this range linearly with the magnetic field strength. And we also found that they present amplitude, for example, for the 300 Gauss case, a peak amplitude of around 25%. So the Zeeman effect produces signals of amplitude of around 1% in the presence of longitudinal fields somewhat larger than 10 Gauss. On the other hand, I draw your attention also to this double peak in the blue wing, which is specifically due to hyperfine structure. And now I continue talking. This was on one hand for the barium line. And now I want to talk about the sodium D line, which has 2 stable isotopes, both of which have hyperfine structure. However, in contrast to the barium D1 line, this is it's the separation between hyperfine structure levels is 1 order of magnitude smaller than for the sodium. And here are some calculations showing the D2 line and the D1, both for a single isotope, so the most abundant one, and considering the 2 abundances, the 2 isotopes with their appropriate abundances. We see that the impact is very small and only in the scattering polarization. So we can safely consider calculations only with the most abundant 39 potassium 39, which makes our calculations a bit lighter. Anyway, what I want to highlight here is this signal in the D1, which would be produced by the key mechanism, but it is of the order of 10 to the minus 3%. This is a tiny signal which is hardly appreciable, and this is because of the small hyperfine structure in the potassium. On the other hand, the D2 line, which is produced by standard scattering polarization, because the upper level can carry atomic polarization, we see that this is much larger. Now, the D2 line is of some interest because this line cannot be observed from the ground because it is absorbed by a strong oxygen telluric line. However, one of the instruments on the Sunrise mission, the balloon mission that flew this July, it could capture the potassium D2. I only caught a glimpse of it the other day, but the results seemed promising. And now some more considerations about this line. So first of all, this is a calculation both with hyperfine structure and neglecting it in the dashed curve. So first of all, if we neglect hyperfine structure, the key mechanism can no longer operate because there is no separation between the various hyperfine structure components. And we simply find basically a depolarized signal. For the D2 line, we find the expected depolarization due to the impact of hyperfine structure. And in the presence of an isotropic magnetic field, here is the sensitivity of the D2 line, in which I'm showing how it's depolarized in the presence of magnetic fields of up to around 15 Gauss. For stronger magnetic fields, we reach the so-called saturation, Hanley saturation, which is due to the fact that the magnetic field can not remove or not further alter the atomic polarization. But still, we see that the sensitivity of this D2 line through the Hanley effect is most apparent in the range between 1 and 15 Gauss. As for the circular polarization, we see, I'm again showing the same realization as before, a horizontal magnetic field and a line of sight that is very inclined, and magnetic fields up to 200 Gauss. Again, their peaks increase linearly with the strength of the longitudinal magnetic field. Although, and they are somewhat larger than the counterparts I showed to you of barium. Amplitudes of about 1% are reached in the presence of magnetic fields somewhat below 10 Gauss. Indeed, in the presence of a 200 Gauss magnetic field, we get amplitudes larger than 20%. And furthermore, the circular polarization can be suitably modeled without accounting for hyperfine structure. Here are the calculations with hyperfine structure and neglecting it, and we get basically the same result, which could be expected because the hyperfine structure is quite small for the potassium, for potassium. Now, this is interesting because we can try to apply the magnetograph formula. Solar physicists will quickly recognize this formula, which is used in our field, in which one can relate the intensity to the circular polarization to the derivative of the intensity, multiplied by the proportional to the magnetic splitting. For this, we need the effective Landy factor, which is often calculated in the absence of hyperfine structure. Indeed, neglecting hyperfine structure, we get the effective Landy factors of 7/6, 42, and of, sorry, this should be 4/3, 41. And indeed, we get a good agreement implying that the magnetograph formula, or the weak field approximation, can be suitably applied to these lines, allowing us to extract information about their about the magnetic fields in around the temperature minimum. And now as conclusions for the barium D2, the barium lines and the potassium lines, I start with the barium D1 line. So because of its large hyperfine structure, the scattering polarization has significant amplitudes in the D1 line, even though only 18% of isotopes by abundance have hyperfine structure. These signals are sensitive to depolarization due to magnetic fields on the order of tens of Gauss. And the value of these signals for my magnetic diagnostics is enhanced by the fact that they appear to be insensitive to the choice of atmospheric model. So we can isolate the magnetic dependence from that of the atmospheric model. The circular polarization signals have amplitudes on the order of 1% for 10 Gauss, a bit less. But however, they are implied by, they are visibly impacted by the hyperfine structure, making it much more difficult to apply the weak field approximation. By contrast, for the potassium D lines, we have a much smaller hyperfine splitting, and so the D1 scattering polarization is basically undetectable. On the other hand, the D2 line, which is produced by standard resonance scattering or standard scattering polarization, has much more detectable signals with amplitudes on the order of point something %. These signals are sensitive to the Hanley effect in the presence of magnetic fields of up to 15 Gauss, 1 to 15 Gauss. And their circular polarizations have amplitudes of somewhat more than 1% in the presence of 10 Gauss longitudinal fields. The hyperfine structure is negligible, and the weak field approximation is readily applicable. And with this, I thank you all for your attention.
Ernest, for your very nice talk. Do we have questions in the room?
Thank you very much, Ernest. All your calculations are based in what you call an isotropic magnetic field, right?
Not all the ones I showed you. So for the circular polarization, I showed you deterministic magnetic fields. So this is why we could get some circular polarization.
For the linear?
For the linear polarization, all the ones I showed you, except for un inciso one with sodium 1 lines, all the others were in an isotropic distribution, yes.
Okay, and then by isotropic distribution, you said, if I remember correctly, that you did a lot of calculations for different orientations?
Yes.
And then you averaged.
In reality, I did this for the sodium D lines. I did not explain this, but for the other calculations I showed you for the potassium lines, which originate deeper, I did this in an analytical way. So first you calculate all the possible rotations, average it over them, and then you get an expression which you apply in the code. And this is based on the assumption that the magnetic field varies at small scales. So at scales much smaller than the average mean free path.
Yeah, that is my question. Is there a difference between a large scale magnetic field variation and then averaging, or a micro scale variation?
There are some differences, but for the especially for the potassium ones I was showing, I would expect no meaningful variation. So you do get some variation in the wings, which are produced by magneto-optical effects. And there, well, since the magneto-optical effects occur typically over they are a radiative transfer effect, and therefore you expect them to occur over a larger scales. And there we do see differences. I have not made the test for the potassium lines, but I would expect the results to be quite similar. But I have to verify this.
Thank you. And another question, it was not clear to me.
Yeah.
Of the potassium lines.
Yes.
the interesting one is the blue or the red component?
For the potassium lines, you mean in circular polarization? Okay, this D2 is the blue, the one with the short, yeah, which is also the detector. Exactly.
More questions or comments? Do you have
Natasha.
Natasha?
Thank you very much for very interesting talk and very interesting results. It's a great job, so congratulations. And one small question, you use 1, 2 level atom or 3 level atom, but what happens if you use more complicated atomic models?
So
my
this is
pet question.
no, this is an excellent question, and it's something that I skipped in the talk. So first of all, to calculate the populations, we first carry out a calculation with only intensity, which is simpler and faster. And for these, we use more complex atomic models. Now, I don't recall for the potassium and barium lines how many levels we considered, but it was far more, to say on the order of 5, 8 different fine structure levels. So yes, we considered the contribution from higher energy levels. And then we fixed these populations and used them in our calculations with polarization. In reality, we had to do this because some of the assumptions that were made in our codes rely on having an unpolarized and an unpolarized lower level. And we fix this population in our calculations. So first we had to calculate it in a more dynamical, in a more accurate way, considering a more complex system. And then when we had a reliable value for these populations, then we did the polarized calculations.
Maybe I am wrong, but I think that Natasha was asking mainly the polarization calculation, whether it is a 2-level atom or it is a more complicated model atom.
Okay.
And the answer is, for the polarization calculation, if you do not take into account the hyperfine structure, is a 3-level atom, J equal 1/2 below and above 1/2 and 3/2. And then once you take into account the hyperfine structure, then it's a really much even more complex multi-level atom calculation. So and this assumption of for sodium D1 and D2 is an excellent approximation for the polarization. And Ernest showed what happens for barium and the impact of the metastable levels.
More comments or questions? Actually, I have a general comment. Because of course my background is more particle physics and microphysics, and I'm very happy to understand part of the language that you're using here in a very different context. You can do fundamental physics with the atmosphere of the sun. So my naive question regards your comment that the matter radiation quantum theory was questioned at some point.
Yes.
But I guess, and if I understood correctly, the solution is environmental, right? You're having quantum mechanics in a statistical system that is the sun atmosphere, and then you have to fold in also the environmental structure of the radiation field that solves the question. Is that the...
In a sense, but this actually required a more sophisticated formalism. So previously, if you assume that the spectral field, the radiation field is spectrally flat,
right,
then you can consider that that in a given scattering process, you can consider the excitation and the de-excitation as statistically independent processes. However, if you want to account for the frequency correlations between them, you can no longer do this, and you have to go to higher orders in quantum electrodynamics interaction.
Quantum electrodynamics.
So the whole theory is a QE. So it's based on first principles of QED.
Right, right. Because we know QED up to fifth perturbative order. We know the dipole, the magnetic dipole of the electron and of the
Yep.
muon with I don't know which obscene precision. This comes from these calculations. So, but then I guess and then and coming to your, I think it's slide 13 or 14, you showed the results of the solution of the D1 or D2.
Yeah. Let me go back. Sorry.
And the agreement is fantastic, no? So
The agreement is, yeah. Well,
so
let's
my,
see.
my
Yeah.
question is, you have to model the atmosphere somehow, no? So
Yes.
I guess this is a fit of your solar model or your model of the atmosphere to the data with the mechanism that explains this with natural
Exactly.
values of things you expect from the magnetic
Exactly.
field, etc. That's what is
Yeah.
happening here.
Yeah.
I
And this,
see.
in fact, was with a quite simplified atmospheric model.
I see.
However, there is a caveat that there are still many observations that we still need to explain. And for this, we will have to go to more sophisticated models, accounting for velocities.
So if I assume that the QED, the radiation matter theory is correct,
Yeah.
so what I learned from these polarization studies is about the atmosphere of the sun. That's what is informing me about this.
Well,
What is
so really,
once you find the mechanism?
So the mechanism is, of course, based on quantum electrodynamics, simply that you cannot stay at first level. So you cannot stay at first order. You have to go to higher orders in order to correctly model this.
Okay, maybe in the coffee you explain this better to me.
Okay.
Comments or questions? Yeah.
You ask a very interesting question, the one concerning the questioning of the quantum mechanics, the validity, no? So which is quite a little bit surprising for the people who did that. But in any case, the story is the following. After Egidio published in Nature the letter and established the paradox, and then other groups decided to make laboratory experiments with a potassium cell, not with sodium, for several reasons, technical reasons. They took a potassium cell, and then they illuminated anisotropically with a laser. And when you illuminate with a laser, then you can you have monochromatic light and narrow band light. So you can excite just individual hyperfine transitions. But this is not, and then they found in the scattered light, when measuring the polarization, a very complicated thing that we don't understand anything. So the standard theory that we apply, the quantum theory that we apply for understanding the polarization of the sun has to be wrong. The quantum mechanics has to be revised, blah, blah, blah. But of course, this is crazy because in a stellar atmosphere, when we illuminate the illumination of the atoms, the radiation that produced in the stellar atmosphere that produces radiative transitions is not narrow band; it is broad band. You excite simultaneously all the hyperfine transitions, so you have to be in the correct context.
Okay. So comments, question. If not, let's thank Ernest again. Okay. Thank you.
No.
And
So thank you.
and of course, you are all welcome to the scientific coffee that is happening now in the cafeteria. Okay, you're welcome.